to the second tutorial in the mini-series on functions at the higher level. Now, in the first tutorial, we were following a young character called Bethany. We looked at how functions could be used to describe her sort of weekday schedule, and those were functions that were mapping between discrete sets of variables. And then we looked at her weekend exploits, climbing a mountainside and tracking her altitude and oxygen content with time. And there we were thinking about functions that mapped between continuous variables, what we might call real variables, real numbers. So in this second tutorial, I'm going to not use any real-world examples. I'm going to be relatively formal as a physicist would ever be in talking about mathematics. And I want to give really three different ways of thinking about functions and talk about some important ideas of the domain and the range of a function. And then in the next tutorial, I'll be talking about composite functions and some very important ideas about not getting bogged down with symbols and thinking about functions as operations essentially on inputs. Right, so in terms of this tutorial, let me try to guide you through three different ways of thinking about a mathematical function. And we're going to just be dealing with continuous variables, real numbers. So if I make contact with the previous tutorial and talk about two sets, we can think about a set of real numbers, and I'm going to call that set capital X, and a given element of that set I'm going to label by the symbol small x. And I want to write down another set here, y, capital Y, and a given element of that set I will label with a small y. And given that these are real variables, we can use the set notation. We can say that the element x is an element of the set of real numbers. Similarly for y. By definition, x is an element of the set x and y is an element of the set y. They're both also elements of the set of real numbers. And what I want to get at in the tutorial right now is whether these sets x and y cover all of the set of real numbers, or are there some restrictions? Now, a function is essentially a mapping. Let me use a different colour to describe this. A mapping from set x to set y, and a given element, little x, will be mapped over to a given element y. And let's be unoriginal and call this function f. And then we would say that y, this element, is the outcome of applying this function f to the element x. So that's quite a mathematical way to think about functions, to define functions. A more pictorial way to think about this is something very familiar to everyone be viewing, is a graph. So we can think about xy axes, x and y axes. Here's x, here's y. This is essentially the number line labelled by a variable x, and this also is the number line labelled by a variable y. And there's the origin. And what one can imagine doing is tracking through all of the elements in this set x and asking how this mapping f, how this function f gives you for each particular x a given y. That's like moving along the x-axis and the function f is telling you essentially what the corresponding y value is for each given x. So for some particular function, one might then describe some curve. So I've just made that curve up there. That's some curve. It actually looks like a cubic function, but we'll come to that later. And this curve would be describing y is the outcome of this function applied to x. Another way to think about functions, but one that I like very much, not to use as a tool, but to use more as a mental model, particularly in teaching if students are having difficulty, is to think of a function as a machine, as an operator, because a function essentially is some operation on this element which produces another element. So a machine is like that. A machine is something that operates on an input. So I sort of imagine it like this. You have a big tube where you put things in, and you have a tube on the other side where things come out. And you have a sort of a black box, and this box has a big label on it which just has f. That is the function f. You put something in, let's call it x, and out comes something which we can call y, but what it actually is the machine applied to the input x. And in the next tutorial, I'm going to be concentrating really on this sort of picture in really helping you to get away from a sort of symbol addiction, if you'll excuse the phrase, around f of x, because that can cause so much difficulty, particularly when one thinks about composite functions and inverse functions. And when I look at these three different representations, you know, I sort of imagine that for those students that are much more mathematically inclined, which really means people that enjoy abstract reasoning, this would be a very, very attractive way to think about functions, and one can go into quite deep analysis here in terms of set theory, which is a large abstract area of mathematics. This is far more pictorial, and I would say that these two pictures coupled together are a more operational and graphical way to think about functions, which one would use in science. One would think in science about a variable, it might be something like time, and then this function might be telling you how a physical quantity, let's say an electric field, depends on time. So the output of that function would be the electric field, and the input would be time, for example. And one might plot that. One might have time in this direction, and in the example, electric field in this direction, and the curve would be a function, the electric field as a function of time. So these are more representations that are useful and appealing to people that have a more applied sort of mindset rather than the more abstract mindset. So sort of more sciencey on this side and more pure mathematical on this side. Right, now my job in the rest of this tutorial is just to give some examples, because I just want to distinguish. For example, you might have a function where every element in this set is mapped to a unique element in this set. And let me just give an example of such a function. And I should have mentioned at the beginning that for this mapping to be called a function, it is necessary that for each element x there is only one destination, only one element in set y that x is mapped to. So let's look at a very friendly and familiar function. Straight line. Let me just say for the sake of concreteness that this is the line y equals 2x plus 1, for example. this would then be the value y equals 1 at the cutting through the y-axis there. And we see here that for every value of x, there is a unique value of y, much like the picture I've drawn here. Let's think about another function that we've encountered before, which is a very friendly function, namely a parabola. Let me use a different colour just for a bit of variety here. Drawing parabolas is not easy. That's not too bad. It's hard to get the mirror symmetry and also the curvature, but that will do for our purposes. And let's say this function is y equals x squared. Well, what's interesting here is that as we've moved along x, first what we see is that we have not made any use of negative values of y. So in this case, this function, this mapping, has mapped the entire set of real numbers in x onto a subset of the real numbers in y, namely only those values of y which are positive. Furthermore, what we see is, because of this mirror symmetry, that equal and opposite values of x will give the same values of y. So for example, let's just imagine for the sake of argument that this was x equals 2 and that this is x equals negative 2, x equals positive 2. Squaring that in each case gives the value 4 for y. And that would be an example of a function where you have two different elements of this set x being mapped to the same element in y. It's still a function because each point is being mapped to one point in y, but in this example we have two different elements being mapped to the same element in y. And this will lead to a complication when we come to think of inverse functions. There is a mathematical language associated with these different sort of possibilities that I'm not really going to get into because it's not something in the Scottish curriculum at the higher level that is examined. So I won't get into that language of onto and 1, 1 and so on. But I think these representations, these graphs and examples can show you the different possibilities. One piece of language I do need to just emphasize is that this set that the function is being applied to is called the domain of the function. And in each of these cases, the domain of the function has been the entire set of real numbers. This set y can have two different names. If we just think of y, for example, as the set of real numbers, this would be called a codomain of the function. But I want to use the word range, which is a more restrictive term, which means the set of values which are the outcome of applying the function to this set. So for this example, the range of the function is the entire set of real numbers in the y set. In this example, the range of the function is a subset of the real numbers, namely the real numbers which are greater than or equal to 0. Now, I want to now look at examples where we have to be careful in how we define the domain of the function. So let me look at a rather nice function, one that you don't see too often actually, at least in the Scottish exam system. They don't seem to give much time to this function. That is the function y equals 1 divided by x. A very natural function to write down, hyperbola. And let's use a different colour for variety. How does this function look? Well, as x becomes very large and positive, y becomes very small. As x becomes very small and yet still positive, y becomes very large, and we have this beautiful shape here. And similarly, if x is negative, y is negative, and we have on the other side. Do you see, though, we have a problem at x equals 0 because, cardinal rule of mathematics, we cannot divide by 0 because that is not going to give us a defined number. So we cannot represent a value for y when x is strictly 0. So in this case, we would have to say that the domain of this function is x is an element of the real numbers, but x is not equal to 0. It has to be excluded at one point to define this function. Let me give another example of a restricted domain. Another very pretty function. You can tell that I like the graphical sort of side of functions here. Let's consider the function y equals the square root of x. So the function is the square root of x. Now here, sort of interesting, I'm going to draw the square root of x in this way. There, that's the function y equals the square root of x. Now you might raise an objection here, because you might say, well, hang on, let's say x equals 4, and then this is fine. I have the output of this function is y equals 2, but you might say, hang on, what about minus 2, negative 2, because negative 2 squared is 4, so a bona fide outcome of the square root of 4 is negative 2. So let me draw what we might call sort of a ghost, like Banquo's ghost in Macbeth. This is another branch. This is an alternative way to represent this function. This would be a negative branch of the function, and I've drawn a positive branch. But because we want to define our functions quite carefully, we're going to say that for a given value of x, they can only have one landing point. So I can't draw both of these branches together and call it one function, because then I would have two landing points. I would have a multi-valued function. So we're just going to draw this positive branch here, but we can keep in mind that we could alternatively have drawn this negative branch down here. There's going to be a very interesting relationship between these two pictures when we talk about inverse functions, and I think you can already see how similar these functions look. Now, the thing I wanted to say about this function, though, just looking at the blue part of the function, is that regardless of one or two branches, there is no possibility of applying this function to negative values of x if this range, or even if this codomain of the function is has elements which are real. We've come across this before in talking about the discriminant in quadratic functions. We are not able to give a meaning to the square root of negative numbers if we are considering real variables. So in this case then, we would say that the domain of this function is restricted to, again, x is real, but now it's restricted to x is greater than or equal to 0, and we're not able to apply this function to negative values of x. Let me just give one more example, a tricky one actually. This will be a good test for you if you're into sketching functions. I just want to sort of combine these two difficulties in one function. So let's consider the function y equals, and let me just reinforce the idea that this is indeed a function. So y equals f of x, and that function is the square root of x plus 1 divided by the square root of 1 minus x. It's kind of an interesting function. Right, well, let's have a look at this. If x is greater than 1, I've got difficulties because this square root will have an argument that's negative and I can't get a real number from it. So x equals 1 is going to be sort of an upper boundary here in some sense. If x is less than negative 1, I have the same problem with this square root because I will be looking at square roots of negative numbers. So this function, if defined to be mapping to a set of real values, must be between negative 1 and 1. Let's sketch it. For x close to negative 1, this part of the function is where the action is, and it's going to be a square root shape. We get a different colour. And then we can see when x is 0, the value is 1, so it's going to pass through the value 1. And as x approaches 1 from below, it's going to diverge. So this function will look something like that, roughly speaking. And it diverges off to infinity here. Right, domain. Let's describe the domain of this function, and we have to be quite careful. Well, we're saying that x is real, and here it's fine to say that x is greater than or equal to negative 1. But for this square root here, we can't say that x is less than or equal to 1. All we can say is that x is less than 1 because x is not equal to 1. We can't include the value 1 in our domain. So the domain would be x is real. If I just shift this up a wee bit, and then we would say negative 1 is less than or equal to x is less than 1. Would be the correct description of the domain of this function. Right, so that's quite a lot of graph sketching there for these different functions. It's actually quite enjoyable, I have to say. I haven't done that for quite a while. Quite pleasant to sketch different functions. The important points from this tutorial are to have an appreciation of this more pure mathematical way to define functions in terms of mapping between one set and another set, to be able to appreciate that this can be graphically represented as what we commonly call a graph on an xy set of axes, and on also thinking of a function as a machine that operates on an input and gives an output, and that's going to be very useful for us in the next tutorial. And then I just gave some examples of different functions, quite common functions, a straight line, a parabola, a hyperbola, square root, and then a rather more devious function here, a quotient of two different square roots. Just to give you a sense of how you can have functions where you have sort of one-to-one mapping between two sets. You can have functions where you have a one-to-many mapping between two sets, and where the range of the function is a restricted set of real numbers, here just positive real numbers. You can have functions where the domain has to have an excluded point because of a problem with infinity that we can't divide by 0. We can have functions like square root functions where we have to exclude whole ranges of x because we require the outcome to be real. And then here we have sort of a combination where we had to think carefully about square roots but also about divergence and had to exclude the point x equals 1. So I hope that's given you a sort of a sense of how to think about functions and domains in particular, and hopefully you'll be able to do examples from past papers in your exam boards to get more practice both in drawing functions and thinking about domains and ranges. Right, hope that's helpful, and in the next tutorial we will be talking about different arguments of functions and composite functions, and I'm going to actually give a fourth tutorial in this series on inverse functions. So I'll see you then.